Episode 8. The CPU Scheduler. Scheduling Algorithms. Welcome back. In the previous lessons, we discussed creating, terminating, and synchronizing processes. Now, imagine a long queue of processes in the ready state, all waiting to be executed, but we only have one or a few CPUs. The key question is, which process should run next? This decision is made by the CPU scheduler, and the rules it follows are called scheduling algorithms. Scheduling is critical because its efficiency directly impacts system performance and responsiveness. 1. Goals of CPU scheduling. Before diving into specific algorithms, we must understand what we aim to optimize. A good scheduling algorithm balances the following goals. Maximize throughput, the number of processes completed per unit time. Maximize CPU utilization. Keep the CPU as busy as possible. Minimize waiting time, the time a process spends in the ready queue. Minimize turnaround time, the total time from process submission to completion. Minimize response time, the time from a request until the system produces the first response, crucial for interactive systems. No single algorithm can optimize all criteria simultaneously. Choosing the right one depends on system type: batch processing, interactive, or real-time. Today, we'll cover two fundamental algorithms: first come, first served, FCFS, and round robin, RR. 2. First come, first served, FCFS. The simplest scheduling method. Like a queue in a supermarket, whoever arrives first gets served first. Mechanism. A simple FIFO queue. When a process becomes ready, it is placed at the end of the queue. The scheduler always picks the process at the front. Example: 3 processes with burst times: P1, 24, miss; P2, 3 mins; P3, 3 minutes. If the order is P1, P2, P3, P1 runs 0 to 24, waiting time 0, P2 runs 24 to 27, waiting time 24, P3 runs 27 to 30, waiting time 27 average waiting time 0 to 0 plus 24 plus 27, 3 pa 17 nedams. If the order is P2, P3, P1, P2 runs 03, waiting time 0 to P3 runs 36, waiting time 3, P1 runs 6 to 30, waiting time 6 average waiting time 0 plus 3 plus 6, 3 messes. Weakness, the convoy effect. A long process, like P1, delays shorter ones, similar to a slow truck blocking faster cars on a highway. Note, FCFS is non-preemptive. Once a process has the CPU, it keeps it until completion. 3. Round robin, RR, designed for interactive time-sharing systems, RR improves fairness and response time compared to FCFS. Mechanism. Define a time quantum, 10 100 meters typical. The ready queue is still FIFO, but each process can only run for one quantum. If it finishes before the quantum ends, it releases the CPU. If it's still running, the CPU is preempted, its state is saved, and it is sent to the end of the queue. Example: with P1, 24 mm, P2, 3 mm, P3, 3 mm, and quantum Q 4 mm. P1 runs 4 mm, 20 left, goes to end, Q, P2, P3, P1, P2 runs 3 mm, done. Q, P3, P1, P3 runs 3 ms, done. Q, P1. P1 continues in cycles until completion. Here, P2 and P3 have short waiting times and the system responds faster overall. Trade-off: large quantum behaves like FCFS. Small quantum, too many context switches, wasting CPU time. Conclusion: FCFS. Simple but causes convoy effects. Suitable for batch systems where waiting is less critical. Round robin. Fair and responsive, widely used in modern OS, requires careful tuning of time quantum. Beyond FCFS and RR, other algorithms exist: priority scheduling, shortest job next, and more advanced hybrids. In the next lesson, we'll shift to communication. How can processes exchange information safely and efficiently? That is the topic of Inter-Process Communication, IPC. See you then.